Welcome to the final session, the final talk in this morning's, the first session talks. So today we're having a large collection of people working this project, but only two presenting. This will be Joseph Buchanan, Eric Pelttari from Illinois State University, talking on d-modular labels graphs.
So my name is Eric Pelttari, and I am a pre-service teacher from Northern Illinois University. And we did our research at an REU here at Illinois State last summer under the direction of El-Zanati. The people that were working with Joe is here speaking with me as well. And then Ryan Bunke is also from Illinois State University. Greg Rasmussen is a high school teacher at Roanoke Benson. Alexander Sue is a student at U High, and Stacey Garris is a student at Illinois Wesleyan University. Now, before we start, we need to get some definitions. So for graph decompositions and designs, now if we let G and H be graphs, such that G is a subgraph of H, a G decomposition of H is a partition of the edge set of H into subgraphs isomorphic to G called G blocks. We also call these HG designs. And if we let the vertex set of Km be the integers mod m, and let G be a subgraph of Km, by clicking G, we applying the isomorphism I goes to I plus 1 to the vertex set of G. We'll see some examples of clicking. That's going to be a very important concept. G decomposition of Km is cyclic if clicking G preserves the G blocks of the decomposition. So here's an example of a cyclic decomposition. We're going to have a cyclic K3 decomposition of K7. So if you notice, we're going to start with a K3 here, from 0 to 1 to 3. Now if we click that around one time, we'll have another K3, this yellow one. And if we continue clicking that all the way around, you notice we have all of the edges of a K7. So that makes it a cyclic K3 decomposition of K7. Now I said edge length is very important. So if we place the elements of the vertex set of Km around an m-gon, then the length of an edge is going to be the shortest distance around the polygon. So from 0 to 2, the shortest distance is going to be 2, so the length is 2. However, from 2 to 6, if we go around the bottom, that's a length, but it's a distance of 4. Around the top is a distance of 3, so we take the shortest, so the length is going to be 3. Now if we click that, it doesn't change the length of the edge. You notice this is still a length of 3 here. Also, if we let m equal 2t plus 1, then we have an odd number of vertices. So then Km consists of m edges of length I for each I in the set 1 up to t. However, if m equals 2t, so it's an even number of vertices, then Km consists of m edges of length I for each I in the set 1 up to t minus 1 and t edges of length t. A lot of the results on graph decompositions come from a conjecture of Ringo, which says that every true with n edges decomposes the complete graph K2n plus 1. And if you'd like to be famous, maybe somebody can answer that conjecture, either in the positive or the negative. Alex Rosa came up with some labelings to help him attack that conjecture. The first is the row labelings. And in this case, your vertex labels have to go from 0 up to 2n. You have one edge of each length between 1 and n. And it produces cyclic K2n plus 1g designs. Sigma labelings do not allow wraparound edges. Beta labelings, which are probably the most well-known, also known as graceful labelings. In this case, the vertex labels go from 0 up to n. And then alpha labelings, which are very useful. In this case, however, G has to be bipartite, and all the vertex labels from one part in the vertex partition must be less than those in the other part. And here you'll see in the top part here, the vertex labels go from 0 to 3, and in the bottom they go from 4 to 8. So all the ones in the top are less than those in the bottom. This will yield a cyclic K2nx plus 1g design. It does have limitations. It's restricted to bipartite graphs only, and not all trees are going to admit your alpha labels. Now, most of our research was actually in row labelings, and Joe is going to give some examples of those.
So with our research, what we were mostly concerned with was decompositions of complete multipartite graphs. So we have some notation here. The complete multipartite graph, Kr cross D, means that we have R parts of size D, R parts of D vertices each. And we can obtain this from the complete graph, KRD, basically by removing all the edge lengths that are a multiple of R. So for example, if we start with K15, the complete graph on 15 vertices, and we remove all the edges that are a length of 5, it's going to leave us with a K5 cross 3. Here's a graphical illustration. We have our K15. We're taking away all the edges that are a length of 5. You can see those edges were bolded. So if we look at just those edges that we want to remove, that gives us 5K3s. So to help us see this, we take those 5K3s and color their vertices. Now if we put those back in the K15 and actually take away those K3s, you can see that this leaves us with 5 parts. Each of the colors represents a part, so we have 5 parts of 3 vertices each, a K5 cross 3. Another example of this, if we have a K40 and we remove all the edge lengths that are a multiple of 4, this leaves us with a K4 cross 10. So what this means is if we take a graph G that has 15 edges, we embed it in a K40, we want edge lengths 1 up to 20, since K40 has 20 edge lengths, but we don't want the multiples of 4. This is going to give us a starter for a cyclic G decomposition of K4 cross 10. An example of this is the famous Peterson graph. It has 15 edges. We've put it in K40, but we've skipped all the edge lengths that are a multiple of 4, and so this gives us a starter for a cyclic P decomposition of K4 cross 10. This idea leads to the concept of d-modular row labelings. So if we let G be a graph with n edges, let D be a divisor of 2n, and R equal 2n over D plus 1, then a d-modular row labeling of G is an embedding of G in KRD that gives us one edge of each admissible length that's not a multiple of R. So d-modular row labelings give us, not only as we said, a starter for a cyclic G decomposition of KR cross D, but we also get more. And this is due to a theorem from Professor El-Zanati and others, which says that if we have G, a z-partite graph with n edges, and D is a divisor of 2n, R equals 2n over D plus 1, if G admits a d-modular row labeling, then there exists a cyclic G decomposition of KR cross DT for every positive integer t that's relatively prime to z minus 1 factorial. So an example of this, we have a 12 modular row labeling of C6. C6 is a bipartite graph. Since it's 12 modular, we're embedding in a K2 cross 12, which means we're skipping all of the even edge lengths. So suppose we want T to be 3. Okay, so we want a cyclic 2 cross 36 C6 design. What we do is we take 3 copies of our C6, and we leave all the labels in set A the same. Also, to our first copy, we're adding 0 to the labels in B. Basically, our first copy, we're leaving all the labels the same. However, in the second copy, we add 24 to the labels in B. And in the third, we add 48 to the labels in B. And if you notice, this gives us each of the edge lengths we want, 1 up to 35, skipping the even edge lengths. And this gives us starters for a cyclic K2 cross 36 C6 design. An example of a tripartite graph, we have a 9-modular row labeling of C5 union C4. Since it's 9-modular, we're embedding in K3 cross 9. We're skipping all of the edge lengths that are a multiple of 3. And suppose we let T be 3. We're looking to embed in a K3 cross 27. Now here, since we're working with the tripartite graph, since z minus 1 factorial is 2, when we're choosing values of t, we need them to be relatively prime to 2, which means that we can only pick odd values of t. So, like before, we take 3 copies of our C5 union C4, and we leave all the labels in set A the same. And like before as well, we add 0 to the labels in B and C. Now in the second copy, we add 27 to the labels in B and 54 to the labels in C. And in the third, we add 54 to the labels in B and 27 to the labels in C. And Eric is going to talk more about our particular research.
So that was all the background to what we actually did this summer. Now, there are some results on d-modular row labelings already. They've been investigated for several different classes of graphs. They've been investigated for complete graphs, complete bipartite graphs, single cycles, paths and unions of paths, and many other classes of graphs as well. So we asked, okay, it's been done for single cycles. Can we do it for the union of 2 cycles? Is such a thing even possible? Well, yes it is. And here is a breakdown of what we did this summer. So we've got a chart here that's going to list all the different cases for the union of 2 cycles. So if we have a cycle Cm union with the cycle Cn, those are going to break down in different cases based on m and n mod 4. In the first case, when both m and n are congruent to 0 mod 4, what we're going to have is a cycle that's going to be C4R union C4S, where R and S are non-negative integers. Now this gives us some different divisors. The divisors that we've listed here are not all of the possible divisors. There are other divisors such as 1 and 2, which have already been investigated. And there are other divisors, but these are the only definite divisors that will always work no matter what our values for R and S are. If we look at the next case, when M is congruent to 0 mod 4 and N is congruent to 1 mod 4, in this case you notice we only have one definite divisor besides the divisors of 1 and 2, which have already been studied. So each case is going to have a different number of divisors. Now for each of those divisors we found patterns, and I'm going to show you a couple examples for the case where M and N are both congruent to 2 mod 4. We're going to look first at this divisor, 2 times R plus S plus 1, and then at the divisor, the fixed divisor of 8. So in the first case, we're going to have, and we came up with general patterns that will work for any value of R and S, any non-negative integers. But here's a specific example. When we have a C18 union C14, so R equals 4 and S equals 3, and we're going to embed that in a K5 cross 16. Now since it's in a K5 cross 16, that means we're embedding this whole thing in the complete graph K80, which also means our longest length would be 40. However, we're skipping multiples of 5. Since 40 is a multiple of 5, our longest length is actually going to be 39 right here. And if you notice, we go from 39, this length is 38, this is 37, 36. We skip 35, since that's a multiple of 5. We go all the way down to our shortest length of 1 right here. So we have all the lengths from 1 up to 40, skipping multiples of 5. We can use that. This is a specific example, but we came up with a general pattern that will work for this divisor for any value of R and S. Now, that gives us starters for cyclic decompositions. So we can use these starters to decompose an infinite class of graphs. Similarly, in this case, we're working with the same 2 cycles. The only difference is we're switched to a divisor of 8, fixed divisor. So again, we're going to be skipping multiples of 9 in this case. So you notice our longest length is 35, skipping the multiple of 36 down to our shortest length of 1. So really, what we were doing this summer is just finding all these different patterns. And the way it worked out, for each divisor, there were different patterns. And sometimes for our divisors, we had multiple patterns. So we have all of our divisors here. We ended up with about 60 or more different patterns. What that means, using those patterns, we can take any 2 cycles, the union of any 2 cycles, and we can come up with an infinite class of graphs that those 2 cycles will decompose. And that was the main focus of our research. Just saying, give us any 2 cycles, we can tell you a complete multipartite graph that those cycles